This is our test bench report about the final project of the subject digital design with VHDL. First of all, we are going to explain all the code that give us all of these uh, nice signals. First of all, we have our inputs and output signals, the clock of the basis 2 FPGA working on 50 megahertz, the reset button, the asynchronous reset button, the display that shows the results of the degrees, and vector that helps us with the multiplexing of the displays, the input of the ADC, the analogic to digital converter, and an output that is gonna give us the PWM signal to the servo motor. In this case, in the test bench, it's the same. We have all the same variables and we have all the signals. It's more like for syntaxes. We start all the signals in the most common values on zeros, and those are outputs. Then we just assign like the syntaxes. And this is an important part of the code. We have the clock that is gonna change to 0 to 1 each 10 nanoseconds, and we have a wait for 20 nanoseconds. This is one period of, no, yes, this is one cycle. This is one cycle of our 50 megahertz signal of clock. So we make this signal like in this process, because if we do like manually, we're gonna have like a lot and a lot and a lot of changes between 0 and 1, and that's not easy to code. And we have all the changes for trying different values of the ADC and different degrees, and then reset button. And of explain all the code, we are going to analyze the signal waves in the simulation. So the first part is to analyze the first rising edge that we got it until 10 nanoseconds. And we have an integral value in the ADC of 10. That means that we are in the first range, 0 to 38. So we are in 0 degrees. We are in the hundreds, hundred anode vector, and we are showing the same as the 100 signal. And because we are in 0 degrees, we have 0 in the signals in the tens. Then we analyze the second case until for milliseconds and 10 nanoseconds, because we are analyzing the first rising edge clock. So we are showing the tens display, and because we are showing the tens display, we have the same as the signal D in the display, and we have an integral value of 39. So we are showing 10 degrees, as we can see in the code. The fifth case, we got it until 8 milliseconds, and then of the rising edge clock. So we are not analyzing the units vector or the units display. So in the units display, we have always a 0, because we are making steps to 10 to 10 degrees. So we always have a 0 in the units case. We have an integral value of 69. That means 40 degrees. And we have a 4 in our display and a 0 in a 100 display. Our next case we got it until 12 milliseconds, and we have an integral value in the ADC of 117 that put us in 90 degrees. We are in 170, and we have in the tenth signal a 9 form, and our 100 signal a 0, and we are showing the 100 signal, so we have a 0. The next case, we got it until 16 milliseconds, and we are showing the 10th signal or the 10th display. We have in the 10th signal a 0, because in the ADC we have an integral value of 196 that put us in 100 degrees. So we have in the display the same as the 100, so we have a 0 and a 1 in our 100 signal. In the next case, we got it until 20 milliseconds, and we are analyzing the hundreds and displays, because we got it in our anode vector. And in the 100 signal, we have 1, because we have more than 100 degrees. We have in the ADC an integral value of 174 that put us in 150 degrees, and we have a 5 in the 10th signal. We have the last case of our ADC. We are in 180 degrees, so we have an integral value in our ADC of 202. We are showing the 10th display, so we have the same in the display output and our display signal. We have a 1 and in hundreds and an 8 in signal in our 10th signal. So we are gonna analyze the next case, if we use the reset button, all the past moments we got the reset button in 0, and if we push it in like in person, we have a 1 in our FPGA input. So all our signals goes to the start value or the default value. We have a 0 in our signal and a strange value because we don't control the signal C. We put all the displays on and show a dash in all displays. And in ADC value, that doesn't we doesn't care about it in this case. And like we can watch in this part of our simulation, we have all the counters in 0, and also the PWM signal of our servo motor goes to 0. That we have to analyze is the PWM signal. We have or we want a 50 hertz frequency with a duty cycle of 1.5 milliseconds. So if we see in the simulation in the 10 nanoseconds moment and in the 1.5 millisecond moment, we have all our signal on. So that means that our servo motor is gonna put in 90 degrees, and then of 90 milliseconds, we complete 1 second, and we have our PWM signal exactly that we want.